When you've discussed acidity before, you've done so by looking at the pH of a solution. And you know that a pH that's less than 7 is an acidic solution, pH that's greater than 7 is a basic solution, and a pH of 7 is a neutral solution. But now we know that acidity actually relates to the quantity of hydronium ion in solution. Right? We actually care about this H3O+. And the basicity or the alkalinity of a solution actually relates to the hydroxide ion concentration of the solution. So really what we should be concerned about should be this hydronium and hydroxide ion concentration. But those concentrations vary so drastically over such a huge range that the pH scale, which is logarithmic, compresses the values, placing them between easy to understand 0 and 14. At this point in chemistry, though, you need to know how to convert between a hydronium ion concentration and a pH, and that's what this lesson is going to be about. So let's say that you know the hydronium ion concentration of a solution, but you want to figure out what the pH is. Well, the way that you would do that is you would take the negative logarithm of the value. So whatever the concentration is, you take the negative log of it, and that will give you the pH. What if you want to go the other way? Well, you need to do the inverse of a negative log, which is taking 10 to the power of the negative value of the pH. Now let's try one of these. So if I have a solution with a pH of 5.34, I want to figure out the hydronium ion concentration. How do I do that? Okay, well, I know the pH value, trying to figure out hydronium, so that means that I'm going this way. I'm following this purple arrow. So I need to take 10 to the negative value of the pH, and that will give me the hydronium ion concentration. So my pH value is 5.34, so I need to take 10 to the power of the negative 5.34. I need to make sure to use my negative symbol here instead of my subtraction symbol. That will give me an error. And so the answer it spits out is 4.5708 E negative 6. So this is scientific notation, times 10 to the power of negative 6. So let's write my value down here. It's 4.5708 and some more change times 10 to the negative 6. Now this is a concentration, so the units are coming out in units of moles per liter. Now what do we do with sig digs here? Sig digs work a little bit funny when I'm doing logarithms. So what I'll do is I'll take the number of decimal places that I have in my pH, and that's going to become the number of sig digs that I'm allowed to report in my concentration. So I have, it's not just a straight sig digs here, right? I've got 2 decimal places, so that means I get 2 sig digs in my concentration. So I'm going to round this value to 4.6 times 10 to the negative 6 moles per liter. And let's write this sig dig rule down for ourselves. So for sig digs here, if I have my pH and I'm going to my concentration, or vice versa, my decimal places, the number of decimal places that I have, needs to correspond to the number of sig digs that I have in my concentration. And if I wanted to go the other way, I would just take the negative logarithm of the value. And we can check and make sure that that's going to work with the value that I've plugged in here. So if I take the negative log of this, it should give me back my pH of 5.34. So let's try it. Let's take the negative logarithm of my answer. So that's going to type in my 4.57 times 10 to the negative 6. And that gives me back 5.34. Okay, that works. So the pH scale measures how acidic something is, right? pH of 7 is neutral, This was a pH of 5 and a bit, so that's somewhat acidic, about as acidic as coffee. Vinegar can get down to a pH of 3. Your stomach acid can get even lower, and a battery, lead acid battery, is going to be close to a pH of 0. Now, what if we want to measure the basicity of something, though, or the alkalinity of something, how basic something is? Well, there's kind of a shadow scale, and it's called the POH scale. And the POH scale is not measuring the power of hydrogen, but it's measuring the power of hydroxide. So we have the most hydroxide at these extreme high pHs, and we have the least hydroxide down at the very acidic conditions. So this scale is going to count backwards. Neutral's in the same spot. Neutral's still at a pH and a POH of 7, but a pH of 6 would correspond to a POH of 8. 5 in the pH would be 9, right? And we're going to count backwards here until we get to a battery. If it's got a pH of 0, it would have a POH of 14. And we can keep counting the other way here. So something that's slightly basic, like ocean water, would have a POH a little bit less than 7. Hand soap would have a POH of 4. Something very basic like bleach has got a pH of 1. And lye, which is sodium or potassium hydroxide, has got a POH of 0. It's very, very basic. So you see that these scales are just opposite, right? POH is the power of hydroxide. It's measuring how basic something is, and it reads opposite to the pH scale. Okay, so that means we've got a whole other set of scales that we need to figure out here. There's a POH scale, and we can use that to figure out a hydroxide ion concentration. So to get back and forth here between a pH and a POH, well, if the scales are opposite, you'll notice that the two numbers always will add to 14. So at neutral, 7 plus 7 is 14. 5 plus 9 is 14. 2 plus 12 is 14. 0 plus 14 is 14. 12 plus 2 is 14, right? These are always going to add to 14. So that gives me a formula to allow me to convert between pH and POH. The pH plus the POH will always equal 14. And then on the POH side, it's not too scary because it works the same way as the pHs here. So if I want to go from a POH to a hydroxide ion concentration, I take 10 to the negative POH. And if I want to go from a hydroxide ion concentration to a POH, I take the negative log of the hydroxide ion concentration. So that means that with this formula system, I can actually get from anywhere on here to anywhere on here, right? If I start with the hydronium ion concentration, and I wanted to figure out the hydroxide ion concentration, well, I could take the negative log, then I could subtract from 14, and then I could take 10 to the negative POH. So you can follow the arrows from where you're starting from to get to where you want to go. So let's try one that's a little bit more complicated. A solution has got a pH of 3.4. What is the POH and what is the hydroxide ion concentration? Okay, so we're starting with a pH. I want to figure out the POH and then the hydroxide ion concentration. So let's start with the first bit here. My pH plus my POH will always sum to 14. So if I'm trying to figure out the POH, I can subtract pH. These guys are going to cancel. That means that the POH will be equal to 14 minus the pH value. So 14 minus 3.4, which we can fire into our calculator. So 14 minus 3.4 gives me 10.6. So my POH here is 10.6. And then if I want to figure out the hydroxide ion concentration, well, I know the POH. To find the hydroxide ion concentration, I need to take 10 to the negative POH. So for the second step here, 10 to the negative POH, so the negative 10.6. 10 to the negative, I can just hit answer and it'll plug in my 10.6. That gives me 2.51 times 10 to the negative 11. Now, the number of decimal places that I had in my original pH, that's how many sig digs I'm allowed here. So I only had one decimal place in my original pH, so that means I only get one significant digit. So this 2 has got to round up to a 3, and don't forget about the times 10 to negative 11. So this will give me a hydroxide ion concentration of 3 times 10 to the negative 11, and don't forget your units, moles per liter. And that's my hydroxide ion concentration.